I'm Peilong Hong from University of Electronic Science and Technology of China. Today, I will share our recent research on light scattering of a single nanoparticle controlled by wavefront shaping. So this is a collaboration with Professor Willem Vos from University of Twente. You can also find our paper in arXiv. Today, my talk includes 4 parts. First, I will briefly introduce the background of nanoparticle scattering. Then I will share our method to describe the nanoparticle scattering. Then I will present our results for the 2D nanoparticle as well as for the 3D nanoparticle. Finally, I will draw a conclusion. So, nanoparticle scattering is a widely studied topic. One of the most well-known nanoparticle scattering is the Mie scattering. That is the light scattered by a Mie sphere. So for this simple geometry, actually we have analytical solutions for both field inside the nanoparticle and the field outside the nanoparticle. But for a arbitrarily shaped nanoparticle, we usually do not have analytical solutions. So actually for these cases, we usually need to do like a full wave simulation. So in case we have the field patterns inside the nanoparticle, then we can do multiple expansion. So for example, we can do the decomposition to get the lowest order, the dipole, the second lowest order, the quadrupole, and octuple, and so on. So even for dipole, we can have electrical dipole, magnetic dipole, toroid dipole. So you see, light scattering by a single nanoparticle could be very complex. It can be a combination of these components. Meanwhile, nanoparticle scattering is also very useful. For example, a single nanoparticle has been used to enhance the second harmonic generation. So in this case, the shape of the nanoparticle and also the size of the nanoparticle should be carefully designed, such that the enhanced harmonic generation is reached at a particular wavelength. So another example is a magnetic mirror. In this case, nanoparticles are arranged in an array, and the size and the structure of the array should be carefully designed, so that the magnetic dipole plays a very important role here. As such, the reflected light from this nanoparticle array is in phase with the incident light. So this is fundamentally different from the electrical mirror we usually used. So in electrical mirror, the reflected light is out of phase with the incident light at the reflecting surface. So these are just 2 representative examples. There are many more examples. So from this introduction, we see light scattering by nanoparticles is very complex and also is very useful. So here, there's a critical question, is that how can we control light scattering of a single nanoparticle? So currently, people usually carefully design the shape and the size of the nanoparticle to realize the control. Here, we consider the question in a different perspective. We assume that we have a nanoparticle at hand, and we want to control light scattering by this particular nanoparticle. So in this case, we cannot modify the size or change the shape of the nanoparticle, but what we can control is the wavefront of the incident light. So here, our question is, can we use wavefront shaping on the incident light to control the light scattering of a single nanoparticle? So before answering this question, I would like to briefly introduce the wavefront shaping technique. So wavefront shaping was previously developed to control light scattering through disordered medium. So for disordered medium, it consists a large number of nanoparticles, so that there are many optical passes for the light to go through the disordered medium to reach a target position. So in this case, wavefront shaping was introduced to control the interference between these different optical passes. So for example, to control the interference to be constructive interference, then we can get the focused light at the transmitted side of the disordered medium. So this is fundamentally different in the case light scattered by a single nanoparticle. So you see for the light scattered to a particular direction, there is only one optical path from the nanoparticle to the observation point. So there is no many optical passes. So we cannot control interference between different optical passes. Then we see whether wavefront shaping is feasible to control light scattering by a single nanoparticle is still an open question. So to answer this question, we employ scattering metrics to describe light scattering by a single nanoparticle. So in this case, we can consider the incident light from this angle range. That means from this range. And we also consider scattered light in the backward direction within the same range, so the backscattered light. Then we can describe the scattering process by using this equation. So here, the column vector L in is used to denote the incident light, and each element of it is used to denote a single incident plane wave, okay, from a particular angle. And SI is the scattering matrix that we used to relate the incident light to the scattered light. Okay, A out here is also a column vector, and each element of it is used to denote a scattered light at a particular direction. So if we know all the scattered light corresponding to each incident plane wave, then we can retrieve the scattering matrix SI. So here for clarity, we define the value of the element of L in and also L out in this way, such that the absolute square of them is equal to the power of light at that particular channel. So you see this is a field strength, and here by definition, delta S is the area of that particular channel. So with the information of SI, we can do singular value decomposition. And it can be represented by three matrices. So here U and V are two unitary matrices, and S is a diagonal matrix. With these three matrices, we can get the information of the scattering eigenchannel. So here, the eigenvalues of these eigenchannels are read from the diagonal elements of matrix S. And the eigenfunctions of the incident light is read from the column of matrix V. And the eigenfunction of the scattered light is read from the column of the matrix U. So with the information of the scattering eigenchannels, then we can answer our initial question, whether wavefront shaping can be used to control light scattering by a single nanoparticle. So what is the result? First, we study the 2D nanoparticle. It's a rectangular nanoparticle. So this is the size of this nanoparticle. We consider the incident light from this angle range, okay, theta here. Then we consider scattered light within the same range, but in the backward direction. Then we do a full wave simulation to get the scattered light corresponding to each incident plane wave. By using this information, we can immediately retrieve the field scattering matrix M here. So by definition, we know the element Li in is the absolute square of it is equal to the power of light at that particular channel. So we use we can derive to obtain this expression for the Li in. Then by using this result, we can get the column vector L in expressed by the column vector, the field column vector E in multiplied by a constant value. Similarly, by definition, we know the power of scattered light at the jth channel is equal to the absolute square of Lj out. So we can also write it down in the field expression that is multiplied by a constant value. Okay, then we can get the column vector L out in this expression. So by combining all these results, we can get the power-related scattering matrix that is equal to a constant value times the field scattering matrix. So with this scattering matrix Si, we do singular value decomposition and get the information of scattering eigenchannels. Then in this table, we list the eigenvalues of these eigenchannels in the descending order for each frequency. So from this result, we see at a single frequency, there are actually more than one scattering eigenchannels. Okay, for clarity, we define a strongly scattering eigenchannel if its eigenvalue is larger than 10% of the first eigenvalue. Then we see in the low frequency range, there are at least two strongly scattering eigenchannels. And when the frequency increases to the high range, there are more than maybe two, to be like three, and even more than three strongly eigenchannels. So this result tells us that a single nanoparticle hosts multiple strongly scattering eigenchannels. And from this result, we can immediately answer our initial question. So wavefront shaping actually can be used to control light scattering by a single nanoparticle. For example, you can use wavefront control on the incident light to excite light to a select eigenchannel. You can even control optical interference between different eigenchannels. Next, we study the case with 3D nanoparticle, that is the Means field. So as I previously introduced, Means field has analytical solutions. So by using this analytical solution, we can get the field scattering matrix M. And by doing similar derivation as that in 2D case, we can get this is a power-related scattering matrix, okay? With the information of Si, we do singular value composition on it, and we get the information of the scattering eigenchannels. So here we consider the frequency of light is 8/9, and we list the eigenvalues in the descending order. So you see there are many strongly scattering eigenchannels for this Means field. So from above results, we see wavefront shaping can be used to control light scattering of both the 2D nanoparticle and the 3D nanoparticle. But previously, we focused on the far field. So sometimes people are interested in the field inside or around a nanoparticle. For this reason, we calculate the field patterns of different eigenchannels. So in this case, we control the wavefront of incident light and couple the light to a particular scattering eigenchannel. To achieve this goal, we use the target wavefront that is obtained by the column vector of the matrix V. As I previously introduced, the column vector of matrix V represents the eigenfunction of the incident light. So in this way, we can couple light to different scattering eigenchannels by choosing different column vectors of matrix V. So we studied several frequencies. These are the results for the field patterns of different scattering eigenchannels. So you see for a single frequency, okay, the field patterns corresponding to different scattering eigenchannel are different. And as the frequency increases, you see the field pattern becomes more and more complex. Moreover, we see there are bright spots, okay, even many bright spots inside or around the nanoparticle. This means we actually couple light to different resonant leakage modes by exciting different scattering eigenchannels. So this is what we see from these field patterns. Finally, I will show the spectra of scattering eigenchannels. So what does it mean? It means we couple light to a select scattering eigenchannel, and then we fix this wavefront, and then scan the frequency. Subsequently, we monitor the ratio of the backscattered power to the incident one. So then we get a curve that is R dependent on the scale frequency. We studied 2 eigenchannels, okay, at the frequency 0.6. So here are the results. You see, for the first scattering eigenchannel at 0.6, and also for the second scattering eigenchannel at 0.6, we see multiple resonant peaks, okay, both in the short spectral range and also in the long spectral range. So this is what we observe, okay, and moreover, we also calculate the field patterns at different resonant peaks. You see, these field patterns are quite different for these different peaks. So it indicates that these resonant peaks are related to different resonant leakage modes of the nanoparticle. So here comes to our conclusion. So we found that first, a single nanoparticle hosts multiple strongly scattering eigenchannels. Second, we show that the scattering eigenchannels are related to different resonant leakage modes of a nanoparticle. And third, we observe that both short range and long range resonant peaks exist for scattering eigenchannel. And finally, comes to our answer, positive answer to our initial question. So wavefront shaping is an efficient tool for controlling light scattered by a single nanoparticle. So this is the end of my talk. Thank you very much for your attention. Your questions are welcome.